Okay, so we're going to do 2 lectures today, and I'll break them up into 30-minute sets. And we're going to look essentially at the factors that affect whether a reaction partitions SN1 or SN2. In other words, if I mix a particular substrate, will I get an SN1 reaction or will I get an SN2 reaction? If I mix a substrate with a particular nucleophile. We saw in class today that there is a consequence to whether the reaction goes SN1 or SN2. That would depend upon it would influence the number of products in the reaction, it would influence the stereochemistry of the products, and so on. So what we need to know is that if we mix a certain Rx substrate with a certain nucleophile under various conditions, are we likely to get an SN1 reaction or an SN2? Well, it turns out that the factors that affect an SN1, SN2 partitioning depend upon, one, the nature of the alkyl group, so the nature of R. In other words, is R primary, secondary, tertiary, and so on. 2, the nature of X, where X is my leaving group, right? 3 is the solvent. Okay? So in terms of the nature of R, we're looking at whether R is methyl, primary, secondary, or tertiary. And in terms of the nature of X, we're going to ask about whether X is a good leaving group or not. And what exactly does that mean? Well, if you remember, in our nucleophilic attack, we have our nucleophile reacting with Rx. And whether it goes SN1 or SN2, what has to happen is that the Rx bond has to cleave. Now, if it's SN1, the Rx bond cleaves to make a carbocation and X minus comes off. If it's SN2, then the nucleophile actually does the attack, but in any event, X minus comes off. So refer to X minus, refer to X as our leaving group. Right? This is called the leaving group. And in some texts you see it referred to as the nucleofuge. Okay? So X is our leaving group or nucleofuge, and we'll call, in fact, the nucleophile, we call this our nucleophile or the entering group. So the nucleophile is the entering group or the nucleophile. X is the leaving group or the nucleofuge. Alright, so we're looking at the factors that affect whether the reaction goes SN1 or SN2. And we say it's the nature of R, the nature of X, and the nature of the solvent. Well, we have to have in our head a model of what happens in the SN1 and SN2 reaction. So what we did in class earlier today was that we said for the SN1 reaction, right, for the SN1 reaction, my Rx cleaves, gives rise to the ion pair, which involves the carbocation. And then the nucleophile attacks this species, and I'm going to write the nucleophile as being negative, and I'm only going to draw a single product. And of course we're aware that we can get both this one plus the enantiomer. And we get the enantiomer assuming that these groups were all different. Okay? That's the SN1 reaction. And this is my rate determining step. On the other hand, in the SN2 reaction, what we have is our substrate. Oh, shoot, this should be X. We have our substrate. Oops, I need my tools. We have the substrate, and I need a bigger one than that, apparently. Eraser. There we go. And oh, for heaven's sake, why am I red now? Because I picked red. Okay, so there's my substrate. So in the SN2 reaction, my nucleophile does a backside attack. X minus comes off. and in a single synchronous reaction, I give rise to my product and X minus. So the SN1 reaction is a stepwise phenomenon. The SN2 reaction is a synchronous reaction. All right, so that's our cartoon, our mechanism of what's happening in the reaction. So let's see what will happen. What would happen if R were methyl? Well, if R is methyl, the SN1 reaction inherently requires the formation of a carbocation. So if I had H's at these three positions, I would make the methyl cation. I can't make the methyl cation. The methyl cation is a highly energetic species because it has no electron releasing groups whatsoever to stabilize it. So I can't make the methyl cation. If I can't make the methyl cation, it means I can't do the SN1 reaction on a methyl substrate. So I'm going to ask the question here now, can I do SN1? Can I do SN2? And for the methyl substrate, SN1 is not possible. What about SN2? Well, the SN2 reaction requires that a nucleophile is able to approach this carbon, essentially to dock at the carbon, to deliver the electron pair. Because fundamentally what is happening in this reaction, in the SN2 reaction, is I have an orbital from my carbon, and that orbital is going to have to overlap with the orbital on the carbon, so the orbital on my nucleophile. So my nucleophile is bringing in 2 electrons. That has to overlap with the orbital on my carbon X bond. So this is a representation of that species. Here's my carbon X bond. I'm using X as a halogen, so that's its p orbital. This is the sp3 hybrid of the carbon. And the nucleophile has to be able to deliver its lone pair of electrons to this orbital on the carbon. So it has to approach within bonding distance. And it's going to be subject to steric interaction if I place large groups on these carbons, on this carbon. But of course, I'm putting H when I'm using methyl. These are just H's. H's are very small, and so the approach of the nucleophile on a methyl substrate is extremely facile. And so even though methyl substrates cannot give me SN1, they can very easily give SN2. So a methyl substrate can very easily give SN2, but it cannot give SN1. And it's kind of interesting, the very thing that denies SN1, a methyl substrate, is what strongly encourages SN2. What about primary? Well, we know, again, primary carbocations are very unstable. A primary carbocation only has one R group that dumps electrons onto the positive site, and one R group does not provide enough electron density to stabilize the carbocation. So methyl and primary carbocations are inaccessible. If that's true, then a primary substrate cannot give the SN2 reaction. So in other words, when I have 3 H's here, I can't get SN1. If I have one alkyl group, again, I cannot get the SN1 reaction, because that would give rise to a primary carbocation which is inaccessible. So I can't do the SN2 reaction, the SN1 reaction on a methyl on a primary substrate. What about the SN2 reaction? Well, in an SN2 reaction, I have a single R group here, but I still have 2 H's. And so even though the R group would provide some steric hindrance to the approach of my nucleophile, certainly it's more than what the methyl will do. It's enough for my nucleophile to wiggle its way in and approach that site and be able to deliver its package. So I can do an SN2 reaction on a primary substrate. It's more difficult than on a methyl, but I can certainly do the SN2 reaction on a primary substrate. Now, there's one little caveat about the primary species. There are some primary species for which the SN1 reaction is possible. And what will those species look like? And the answer is, those are species for which, for example, in the case of benzyl, right? This is a benzyl chloride, for example. That will merely undergo an SN1 reaction because if I lose the chloride, right? If I lose chloride, what I give rise to is the wonderfully resonance stabilized benzyl cation. Right? This species is wonderfully resonance stabilized. Right? And I'm only going to draw 2 resonance forms. You guys, I'm sure, can draw the others. Right? I'll get this species, and then I can move this electron pair in here, and get this one, and so on and so on and so on. So resonance is a very potent stabilizing feature. And so what you end up with is a resonance stabilized carbocation. That's also true for allylic species. So for example, an allyl bromide would very easily undergo SN1, because once we lose the bromide, what we end up with is a resonance stabilized allyl cation. Right? You get the allyl cation, which is resonance stabilized, and therefore the allyl cation is a primary species, but it's readily accessible. So I'm going to put a caveat on our statement that I can't do SN1 on a primary species. I can do it for some primaries if they are resonance stabilized, for example, benzylic or allylic. All right, what about secondary species? Well, a secondary carbocation, we know from previous discussions, is accessible. Because in a secondary carbocation, I'll now have 2 alkyl groups that are dumping electron density onto the carbocationic site, and that is your threshold, at which point your carbocation becomes accessible. So I can make a secondary carbocation, therefore, a secondary substrate will undergo an SN1 reaction. So I'm going to say for the first time, yes, if I have a secondary substrate, I can do SN1. What about SN2? Well, if I have a secondary substrate, it means I've got a second R group, let's say here, and that's going to provide some steric bulk as well as the approach of my nucleophile. And that's going to make it more difficult for my nucleophile to get to carbon. Difficult, but not impossible. It'll have to sort of wiggle its way in, right? But it will be able to navigate and find a trajectory of approach that will allow it to dock with some difficulty at that carbon. So a secondary substrate will allow both the SN1 and the SN2 reaction. What about a tertiary substrate? Well, a tertiary substrate is perfect for SN1 because a tertiary carbocation is wonderfully stabilized because I've got 3 alkyl groups that are dumping electron density towards the electron poor carbon, therefore they strongly stabilize it. So a tertiary substrate will merrily give an SN1 reaction. In fact, if you remember, tertiary substrates are roughly as stable, maybe a little bit less stable, than an allyl or a benzyl cation. Okay? So tertiary substrates will very easily give the SN1 reaction. What about the SN2 reaction? Well, if I put another R group here, the combined volume of those 3 R groups now make it impossible for my nucleophile to approach that carbon. In other words, they physically block the approach of the nucleophile. What we say is those 3 R groups provide steric hindrance to the approach of my nucleophile, and therefore they make the SN2 reaction impossible. So we cannot do SN2 reactions on tertiary substrates. So in other words, if I go up to my table, I can do SN1 on a tertiary, but I can't do SN2 on a tertiary. So what does this mean? It means if you look at the table, then if my substrate is methyl, I'm going to get SN2. If my substrate is primary, I'm going to get SN2, unless it's primary and allylic or primary and benzylic. If my substrate is tertiary, I'm going to get SN1. So just from the nature of the alkyl group, the fate of the reaction is determined in 3 out of 4 cases. If your substrate is methyl anything or a primary anything, it is hell-bent for SN2. If your substrate is a tertiary halide, it is hell-bent for SN1. The only time there's an issue is when your substrate is secondary. If it's secondary, it has the ability to undergo both SN1 and SN2. So you're going to have to look further than just the nature of R to determine what is what fate the system has. So we've looked at the nature of R. So we say that the situation is determined by the nature of R. If you're methyl, your SN2. If you're primary, you're SN2. If you're secondary, SN2 or SN1. If you're tertiary, SN1. Okay. The other factor is the nature of, in fact, I left something out. The other factor is the nature, there's going to be 2, the nature of the nucleophile. Right? So just say the nucleophile. Okay? And then 3 would be the nature of X, and 4 would be the nature of the solvent. Okay? And in fact, I'll tell you what, I'm gonna arrange this a little bit. Well, that's fine. Alright, so what about the nature of the nucleophile? Well, if you look, in fact, I'm going to do this 1 second. So I'm going to change my numbers here. So I'm going to make this factor, let's see, eraser. Oh, eraser, large. So I'm going to make this. Let me go back to pen. Black. So I'm going to make this factor 2 and make this factor 3. I should have just inserted it at the bottom. Okay. So the nature of X. So what is the role of X in these reactions? And the answer is X has to come off, right? So for my SN1 or SN2 reactions to occur, inherent in those reactions is the departure of X. Now in the SN1 reaction, X departs early. In fact, I'm just going back up here. In the SN1 reaction, X departs, right, in step 1, gives rise to the cation in an ion pair. Then the nucleophile collapses, front and back attack, and gives rise to product. In the SN2 reaction, X does not leave until the nucleophile approaches. In other words, what's really happening is that, in essence, the electron pressure from the nucleophile assists in the departure of X. There are 2 electrons in the carbon X bond. Now they are being attracted towards X because X is pulling the electron towards itself. But as the nucleophile comes in with its electron density, it is repelling these 2 electrons towards X. And so what you're having in essence is a push and a pull. So in the SN2 reaction, X does not come off unless the nucleophile, or until the nucleophile is engaged in the process. So in a reality then, I can say that if X is a great leaving group, if X is a great leaving group, it comes off easily, I'm going to get SN1. If X is a good leaving group, right, it comes off with help, I'll get SN2. So really then I can say that great leaving groups, right, great leaving groups will promote SN1, and for that matter, good leaving groups will promote SN2. Now I'm going to make 2 points here. Point 1 is, you notice we're saying promote SN1 and promote SN2. Because the only factor that determines what happens is the nature of R. If R is methyl, there's no promotion, we get SN2. If R is tertiary, there's no issue, you get SN1. So the nature of R defines the course of the reaction. SN1 for methyl and primaries, unless the primaries are resonance stabilized. SN1s for tertiaries, SN2s for primaries and methyls. It's only when you're secondary that it can be SN1 or SN2. The X, the nature of X, doesn't control the reaction. It promotes SN1 or SN2. So if I have a great leaving group that comes off easily and on its own, I will tend to get SN1. I will tend to get SN1. If I have a good leaving group, one that comes off with help, I will tend to get SN2. So let me just make this very clear. What this means is, for example, if I have a tertiary fluoride. Fluoride is not a very good leaving group. Doesn't matter, this is going to be an SN1 reaction. And why is that? Because my substrate is tertiary. If I have methyl and let's say iodide, which happens to be a very good leaving group, which we'll talk about in a second, this is going to be SN1. Why is that? Because my substrate is tertiary. Substrate is secondary. So the nature of R defines the course of the reaction unless R is secondary. So philosophically then, I can say that if I have a great leaving group, I'm going to get SN1. A good leaving group will give me SN2. And that's all well and good, but how do I know when a leaving group is great or good? In fact, how do I know when a leaving group is bad? And in fact, what happens with a bad leaving group? So a bad leaving group is one that simply refuses to come off. And if it doesn't come off, then I'll simply get no SN. neither SN1 nor SN2, because inherent in the SN reactions is the departure of X. And if X will not come off, then there's no SN. So the question is, how would I know when my leaving group is good, bad, or great? And the answer is very simple. Because a leaving group has to be able to do a couple of things. So what should it do? Well, one, it should be highly, well, it should be electronegative. Right? So it should be highly electronegative. Because, and that makes perfect sense, right? What the leaving group has to do is to draw electrons towards itself. That does two things. It makes the R delta plus and therefore encourages nucleophilic attack, but also tends to pull the electrons towards the X so the X can come off with that electron pair. So the more electronegative I make my X, the better a leaving group it tends to be. The other factor is that when X leaves, it has to be a stable species. Okay? In other words, when X comes off, the more stable it is, the more Rx is likely to break up to form it. Okay? So, how are these factors going to play a role in this reaction? And the answer really is quite simple. If I look at some of these leaving groups, what I find, for example, we just talked a second ago that iodide is a fantastic leaving group. It's actually better than bromide, better than chloride, right? Better than fluoride. Well, I know this from our discussions of acids, right? Iodide, the fact that HI is a much stronger acid than HF is linked to two things. One, well, really linked to one big thing, which is the fact that iodine is a much, much bigger atom than fluorine. And the consequence is the HI bond is longer than the HF bond. And therefore this HI bond is long and therefore weak. The HF bond is short and therefore strong. That's reason one. Reason two is, when H plus comes off, I can make I minus, where the minus charge is stabilized over a large area, or I can make F minus, where my minus charge is concentrated in a small area. So in general, the bigger the leaving group, the more it disperses charge, the better it is, the more stable it is, the better it is as a leaving group. So the stability of the leaving group is impacted by all the factors that affect charge stabilization. And that is a combination of resonance, it's a combination of induction, and a combination of size. If you go back to our discussions on acid-base chemistry, which I think we actually taped a lecture on that, those are the factors that affect how the stability of an anion, of anything that's charged. The factors are, how is the charge delocalized? And that is by resonance, delocalization, inductive delocalization, and just shear size. So iodide is a much better leaving group than bromide, better than chloride, better than fluoride. Right? Because iodide, being very big, allows the charge to be delocalized very effectively. So X has to leave as a stable species, and also X has to be highly electronegative. So if I were to take a quick survey of some leaving groups, what I find is the great leaving groups are nitrogen, water, alcohols, iodide, and things like sulfate, right, or bisulfate, and so on. These are great leaving groups. So let's make a quick look at these. How will nitrogen be a great leaving group? And the answer is, well, nitrogen is a leaving group if I look at species like these. Right? These are called diazonium ions. Well, if I look at nitrogen in the diazonium ion, that N is remember, N is one of the world's 3 most electronegative elements. The N here is not only one of the world's 3 most electronegative elements, it is N plus, so its electronegativity is hyped up, and it's also sp hybridized. So it's an sp hybridized N plus, which therefore is going to be super at sucking electrons from R. So this motion of electrons is going to be very, very intense. Secondly, should I break that bond, I'll make R plus, and I'll make molecular nitrogen, which is a wonderfully stable compound. That's why the atmosphere is full of nitrogen. So N2 is, in fact, the world's very best leaving group, because the N is positive and sp hybridized, when it comes off, not only is it stable, but it has no charge to delocalize. N2 is a neutral molecule. Right? Another really good leaving group is water. Right? If I look at this species, which is called an oxonium ion, right? Oxygen is the world's second most electronegative element. Now I've made it O+, and so when the bond breaks, I'll make R+, and I'll make OH2. And again, that's a fantastic leaving group because water is neutral. It's not negatively charged. And so that not only is it neutral, but the O from which it was formed is sp3 hybridized, which is neither here nor there, but it's positively charged and is one of the world's most electronegative elements. So nitrogen, water, alcohols, iodide is a great leaving group because it's just very, very big. And things like bisulfate and nitrate and chlorate are fantastic leaving groups because the minus charge is wonderfully resonance stabilized over a large number of atoms. So the charge is delocalized. So these are what we call great leaving groups. Good leaving groups would include species like, good leaving groups would include species like chloride. Bromide is really kind of between good and great. Carboxylates are good leaving groups, and so on. So these are some good leaving groups. The textbook has lots more examples. What about bad leaving groups? Well, bad leaving groups are going to be species that generally are strong bases. Because if you think it through, if I go back up to the top of the page, right, to what we looked at earlier, iodide is a fantastic leaving group. HI is a very strong acid. Bisulfate is a fantastic leaving group. Sulfuric acid is a very strong acid. H2O is a very good leaving group. H3O+ is the strongest acid that can exist in water. So in general, great leaving groups tend to be the conjugate bases of very strong acids. So it only makes sense then that bad leaving groups are the conjugate bases of weak acids. In other words, bad leaving groups are strong bases. So bad leaving groups are things like hydroxide, alkoxide ions, hydride, R-, and so on, NH2-, right? These are very strong bases, and as a result, they are horrible leaving groups. Okay? So in other words, I can't do an SN2 reaction, right? I can't do an SN2 reaction on an alkane, because to do that would require me to lose hydride, which is a very bad leaving group. I am not going to get any reaction, right? Plus, and really what it comes down to is acid-base chemistry. I can't make hydride from cyanide. That's making a strong base from a weak base. Okay? All right. So if I have a great leaving group, going all the way back up, if I have a great leaving group, I will tend to have SN1. If I have a good leaving group, I'll tend to have SN2. Bad leaving groups, no SN. So if R is methyl or primary, I get SN2. If R is secondary, I get SN1 or SN2. If R is tertiary, I get SN1. If my leaving group is great, I will tend to get SN1. If it's good, it would promote SN2. What about the nucleophile? Well, 5 minutes. What about the nucleophile? Well, the difference between the SN1 and the SN2 reaction is timing, right? Again, in the SN1 reaction, my Rx cleaves to give R plus and X minus, and then the nucleophile attacks to give R nuke. That is the SN1 reaction. In the SN2 reaction, the nucleophile attacks the substrate while it is still bound to X. Right? And we end up with our product. Right? Nuke R and X minus. Okay. The difference, as I said, between the SN1 and SN2 reactions is timing. In fact, I could have said the same thing about the leaving group. in the SN1 reaction, the leaving group leaves early. In the SN2 reaction, the leaving group leaves late. It leaves after the nucleophile has come aboard. The same thing is true for the nucleophile. In the SN1 reaction, the nucleophile enters the reaction late. It enters the reaction after the rate determining step, after the hard work is done. In the SN2 reaction, the nucleophile enters early. The nucleophile does an early attack on R and gives chemistry. Now, let's think it through. In the SN1 reaction, what is the nucleophile attacking? And the answer is, it's attacking a carbocation. It's attacking a carbon that has a full-fledged positive charge on it. Quite frankly, any idiot with a lone pair or a pi pair can attack a carbocation. Right? Carbocations are highly electrophilic. Anything with a lone pair or a pi pair can attack a carbocation. You do not have to be a strong nucleophile to attack a carbocation. You just have to have a lone pair or a pi pair. But in the SN2 reaction, this R is not positive. Now it has a delta plus charge because the X has been pulling electrons from it, but it's only a partial positive charge, a quarter plus, a tenth plus, or whatever. So my nucleophile has to recognize a fledgling delta plus charge and attack that carbon. Now, it's even worse, because when the nucleophile in the SN1 reaction attacks the carbocation, your carbocation is already planar. Your carbocation is flat. So I'm going to draw the carbocation like this. So my nucleophile has to attack either from this plane, where my lone pair of electrons can interact with a p orbital, or from this plane. Right? And not only is my carbon already positively charged, but the groups are not in the plane of attack. So attacking a carbocation is easy, because the carbon is very positive, and approach to that carbon is extremely easy because there are no groups blocking you. On the other hand, to do an SN2 attack, well, that's not easy, because on the one hand, your carbon does not have a full-fledged positive charge, it's a delta plus, and then for heaven's sake, you may have as many as 2 R groups in your way for nucleophilic attack, right? If you substitute a secondary, for example. So doing an SN2 reaction, the nucleophile has to be way more aggressive, way more persistent than in the case of an SN1, because you're attacking a carbon that is not fully positive and that has groups that are in your way. So you have to be a deliberate, intent, aggressive nucleophile to carry the SN2. So in other words, I would say great or strong nucleophiles would encourage SN2, but, modest nucleophiles would tend to give SN1. So in the next lecture, what we'll talk about is what makes a nucleophile great, what makes a nucleophile good. We've already looked at the impact of the R and of the X, that it was the substrate, on SN1 and SN2. We are now sort of examining the nature of the nucleophile in SN1 and SN2. Okay, we'll stop here.